For part A, for AP Problem 6, we're tasked to write the expression for the equilibrium constant, Kc. So we know that it's products over reactants. So it's Kc equals concentration of H2 times the concentration of I2 over the concentration of Hi to the power of 2, because 2 is Hi's coefficient. So question B asks us what is Hi at equilibrium. So if we look at the graph, we can see it starts up here at 1, and then it goes down until it reaches right about here when it levels out. So 0.80 is at its equilibrium. So for part C, we're asked to determine the equilibrium concentrations for H2 and I2. So if we just plug in all of our values into our icebox, we'll have 1.0 in Hi and minus 2x because we have our constant and the coefficient is 2, and minus because all reactants are minus. And we are already given the equilibrium constant, which is found in part B. So it's 0.80. Now, all of our products are 0. So we put 0, 0 for H2 and I2. And it's plus x because all products are plus and the coefficients are 1. So we have the equation here. 1.0 equals 0.80 plus 2x. And if we subtract 0.80 from both sides, we have 0.2 equals 2x. We divide 2 out from both sides, we find that x equals 0.1. So that is the answer for H2 and I2, 0.10 molality. Part D asks us to draw the concentration of H2 on the graph. So we know that it becomes equilibrium at 2 seconds, or right here. So, and the concentration is 0.1, as we found in the other problems. So it would look like this. So for part E, section 1, we're asked to calculate the value of the following equilibrium constants at 700 K. The first one is Kc, so we would do this kind of setup where we have concentration of the reactants, or the products over the reactants. So we have 0.1 for H2 and 0.1 for I2 over 0.80 to the second power, because that's the coefficient. That'll give us 0.016. For part E, section 2, we're asked to find Kp. So Kp equals Kc parentheses RT parentheses to the power of delta n. So we know that delta n is 0 because the products are 2, and 2 minus 2 is 0. So now we have Kp equals Kc RT to the power of 0, and anything to the power of 0 is 1. So it's Kp equals Kc, and we know Kc is 0.016, so Kp equals 0.016. So part F asks us to find the value of Q under completely different circumstances. The difference is that it's now under 1000 K. And it gives us Kc, which is 2.6 times 10 to the negative second power. So to find Q, we have to put it in this format. So we plug all these numbers in that we've already found before, and it'll give us 8.9 times 10 to the negative second. So that means that Q is greater than Kc. So it asks us to determine which direction the reaction will need to shift to reach equilibrium, and whether the equilibrium concentration of Hi will be greater than, equal to, or less than the initial concentration. So we've already said that it's greater than. So this reaction will shift left in order to get the Q value to be the same as the Kc value, and which will be needed to reach equilibrium.